Great. Thank you, Cindy, for the introduction. Welcome everybody today to performance tuning and single processor optimization. As Cindy mentioned, I am retired from UCSD, but I'm coming back to do a few webinars. I really enjoy these topics. Regarding questions, it's a little hard for me to keep an eye on the chat while I'm doing the presentation. So what I'm going to do is periodically throughout the webinar, I'm just going to pause, see if there's anything in the chat to be addressed. So if you don't hear from me right away, I'm not ignoring you. I'm just trying to do my best at the multitasking. So with that, let me go ahead and share my slides. And one of my SDSC colleagues just want to confirm that that you are seeing my slide and that it's advancing.
Yes.
Perfect. Thank you. All right, so as I mentioned today, the topic is performance tuning and single processor optimization. This is part of our advanced computing webinar series. So my name is Bob Sinkovits, the former director of education and training here at SDSC. I have a few links here. These, of course, are available on the slides. In these GitHub repos, I have some examples so that you can go through these exercises on your own. And a PDF version of the slides is also available, and I believe Cindy has already pasted that link into the chat a few times. Okay, so this is only a one hour webinar. That's a very, very short time to cover performance tuning and optimization. So this is highly, highly abbreviated, but we have a longer version of this topic that we cover every year in our Summer Institute. So the slides from last year are available here. And yeah, sorry, I've got a link to the Summer Institute where you can see all of the materials that we present during that week-long event. And then specifically, this second link is for the extended presentation of performance tuning and optimization. So we're going to start off by asking why it's important that we write efficient serial or scalar code. And by serial code, I just mean the underlying serial algorithms that would be maybe part of a parallel application. So first of all, we all want to get our work done quicker. If you optimize your code, it's going to reduce your time to solution. I like to say that challenging problems become doable. Routine calculations can be done more quickly. So I think this is going to make you more efficient as a scientist. So you can get more work done. You could shorten that cycle between submitting jobs and seeing the results. Second, computer time, especially on high-end resources, is limited. So if you're running, and I need to update this, it's no longer Exceed, it's now Access, but if you're running on an Access allocated resource, such as Expanse, you're going to be competing with other users for access. And if you're running on the cloud, you're going to need to pay for that time. And then finally, computing uses a lot of energy. If we can make our calculations more efficient, we could play a small role in driving down our energy consumption. So you might think, isn't going parallel going to save me? So first of all, most parallel applications have limited scalability. I know there's some enormous supercomputers out there that are really meant for hero class simulations. But in reality, most applications are only going to scale to a limited number of cores. Second of all, even if your application did have perfect linear scalability, meaning every time that you double the number of cores and number of GPUs, that the runtime would be cut in half, there's always going to be a more challenging problem that you want to solve. So we're always looking to go to higher resolutions. If you're solving systems of partial differential equations, you want a finer grid size. You might want shorter time steps. You might want to simulate larger systems, more atoms, more molecules, more particles. You want to add more accurate physics into your simulation. You want to extend the duration of the simulations. Or you might want to do more replicates, bigger ensembles, better statistics. So anything that you can do to reduce the runtime of your application is going to help you to do all of these things. And then, of course, the availability of resources and energy usage are still important considerations. So I had recently updated this. The content that I had previously was a little out of date. This is a figure that I got from the United States Data Center Energy Usage Report. So this is work being done at Lawrence Berkeley National Lab. And for 2023, so this is the latest date that they had full data available, they estimated that US data centers used 176 trillion kilowatt hours, or 176 terawatt hours. And that accounted for about 4.4% of US electricity usage. So I know that scientific and academic computing is might be a relatively small portion of that, but still we do use a lot of energy. So I would love to see everybody make their codes more efficient and get more science done per kilowatt hour. All right, so a few guidelines for software optimization. I'm going to say that the prime directive, the most important thing, is that you don't break your code. As you're modifying your code to improve the performance, periodically, run it again, run your benchmarks, make sure that you're still getting the correct results. Before you dive in, profile your code so that you know where to focus your effort. Some scientific and technical applications are enormous now. I know there's a widely used climate and weather code called CESM that I believe the code base is now over 1 million lines of code. So if you decided that you were going to try to improve the performance of that code, last thing you wouldn't want to do is just start at the beginning and go through all 1 million lines. You really need to profile so you know where to focus your effort. As you modify your code, don't obfuscate it. Make sure that it's still readable. And if you do make any changes that are a little bit hard to follow, make sure that you document it well. The second last bullet here is probably the easiest piece of advice to follow, and that is to use optimized libraries whenever possible. So if you were doing linear algebra or eigenvalue solvers or other common mathematical operations, there are a lot of libraries out there that are already very, very well written that are going to be more efficient, more scalable than anything that you could possibly write, unless your area of expertise, say, is linear algebra. And then finally, you need to understand the capabilities and limitations of your compiler, and that's something that we're going to go into in a little bit detail. So how much effort should you put into optimizing your code? So that's going to depend on a number of factors. How heavily used is the code? Is it widely used? Is it a community code? Does the code consume a significant amount of computer time? If it's calculation that is not run very often, only takes a minute to complete, I wouldn't put any effort into that. Is time to solution important? Does getting an answer quickly help you advance science more quickly? Will optimizing your code help you solve a new set of problems? Have you reached the point where most of the computing is now occurring in routines outside of your control, say optimized math libraries? And finally, would your time be better spent doing research? I know that most of you attending this webinar, you are domain scientists, you're grad students, professors, postdocs. You're focused on a particular research problem. So you need to think of how to balance your effort. I would say that spending some time improving the performance of your code is a great idea, but again, balance it against the time that you should be spending on your actual research. Okay, so now getting into the meat of the presentation, we're going to start with profiling your code. So profiling your code is just the process of figuring out where your code is spending most of the time. So as I mentioned, modern software can contain many thousands of lines of code, sometimes more than 1 million lines of code. So you need to profile to know where to focus your effort. And I've found in my experience, I've been doing a lot of software optimization, say over the last 25 years, is that once you profile, you'll often find that the majority of time is spent in a very, very small number of routines. Surprisingly, I find that the tool gprof, which was created back in 1982, is an excellent place to start. You know, in in technology time, 1982 is ancient. It's hard to believe that a tool created back then is still so effective, but I love it. It's always where I begin. It has universal support by all major C and C++ and Fortran compilers. It's extremely easy to use. You simply compile with the -pg flag, you run the code. When you're all done, you're going to have a you're going to have an a.out file, a gmon.out file. You just run gprof, a.out, which is your executable, gmon.out, which is the binary output from gprof, and you'll get your results. And I'll show this in the next couple of slides. And finally, gprof introduces virtually no overhead. Now, I should point out that gprof is not a tracing tool. It's not going to identify bottlenecks in parallel codes, but it's still a great choice for underlying the behavior of the underlying serial code. And I should point out in that second bullet where I have gprof a.out, gmon.out, if you were running an MPI application, so we're running multiple processes, you would get a gmon.out for each process. So let's take a look at some gprof output. So you're going to get two outputs. You're going to start off with the gprof flat profile, which is simply a listing of the functions and subroutines ordered by their relative usage. And if you're lucky, you're going to find that it's really just a very small number of routines that account for a large majority of the runtime. This is useful for identifying the hotspots in your code. So what we're looking at here is a real gprof output. This is from a collaboration that I did with the J. Craig Venter Institute, improving the performance of a flow cytometry code. So don't really worry about the specific names. Just look at the relative usage of each of these. So our flat profile, it starts off, it shows us in the first column the percent time that routine used. So we could see that get number packed data, that first routine, used 68.6% of the time. The routine called main used just over 13%. Quicksort double used about 11%. And then we get some very small contributions from other routines. Get nearest events, a system routine called C_mcopy8, and so on. So just by running gprof, we already know where we should focus our effort, and that's on this one routine, get number packed data. After the flat profile, gprof also gives you a call graph. So the call graph gives you some additional levels of detail, such as the exclusive time spent in a function, the time spent in all of the children, the functions that routine calls, and statistics on the number of calls from the parent. So I find that the call graph is not quite as useful as the flat profile, but it does give you some insight into the code. So we could see here starting off that routine main, you'll see that it accounts for 96.9% of the time. And that is a combination of the time actually spent in main and all of the routines that it calls. So you'll notice that it's broken up into self and children. So self is the actual time spent in main. Children is the time spent in the routines called by main. And no surprise here, we could see that the routine get number packed data, which is called about 399,000 times from main, accounts for most of the time, and so on and so on. So once we've profiled our code, we can dive in, we can start optimizing routines, but I'm going to say it's really important to go back and reprofile your code after you've done a round of optimizations, since new hotspots may have emerged. So in this case, I was able to improve the performance of get number packed data so much that it is no longer the most time-consuming routine. You'll see that it's now dropped down to second place. Instead of using 68% of the time, it's now using 26% of the time. And the routine main, which previously used 13% of the time, is now using 41% of the time. Now, this doesn't mean that main has become any slower. It just means that the relative contribution of the time spent in main is so much higher now that we're able to improve the performance of get number packed data. So again, there's a lot of progress that you can make just using this very, very simple gprof tool. Now, you might be wondering, it's been 40 years since gprof, actually a little bit more than 40, I guess, 43 years. Is there anything new? And there are other tools out there. The one that I'm going to recommend if you're working on Expanse is the AMD muprof tool. It gives you more detail than gprof, including low-level information in things like cache misses, branch miss predictions, and so on. And uprof is going to be covered in a future training topic. Now, one of the drawbacks to uprof is that it is proprietary. You're only going to be able to use that if you're running on AMD processors. If you're working with Intel processors, there's a routine called vtune. And if you're working with NVIDIA GPUs, there's a tool called Insight. All right, so I'm just going to take a quick look at the chat, see if there are any questions. Oh, comment from Vinod Gupta, is it 176 trillion kilowatts watts? Sorry, yeah, thank you for catching that. It's 176 trillion watts. That was a typo there, and I'll be sure to fix that when I post a new version of the slides. So let me go back to the presentation. All right, so we're going to actually dive into into performance tuning and optimization techniques. But before we do, we need to talk about a distinction between compute-bound and memory-bound codes. So we tend to think when we are working with software that we're really limited by the rate at which we can do the math, at which we can do the calculations. But for many, many scientific and engineering applications, they're really memory-bound. That means they're limited by the rate at which data can be delivered to the CPU. So over time, CPUs have gotten faster, memory has gotten faster, but CPUs have gotten faster more rapidly than memory has. So memory is always getting a little bit further away in terms of clock cycles. So our goal when we're working with the memory-bound code is to apply cache level optimizations so that the CPU is not starved for data. Now, compute-bound codes is where the performance of the processor is the limiting factor. Data can be delivered fast enough, but the processor can't keep up. So our goal is, if we're working with a compute-bound code, is to reduce the amount of computation done on a given piece of data. And in real applications, we're going to find that there's often a combination of compute-bound and memory-bound kernels. So we're going to talk just a little bit about the computer memory hierarchy. So between registers, which are very, very fast, they're actually part of the CPU, that's where data resides, that's immediately available on the next clock cycle for use by the CPU. Between registers and our hard disks, either hard disks or SSDs, we have multiple levels of hierarchy. So on the processor, we have 3 levels of cache, L1, L2, and L3 cache. For as long as I could remember, all modern processors have these 3 levels of cache. As we go down in the hierarchy, the caches become larger, but they become further away from the CPU. So registers, are going to be extremely fast. I believe that we have on the order of hundreds of registers. We could hold maybe 100 words or so of data there. The L1 cache has a latency on the order of a few nanoseconds, and they're typically about 10 kilobytes. L2 cache is a little bit larger, maybe on the order of hundreds of kilobytes, but it's further away from the CPU. If data resides in L2 cache, but it's not in L1 or the registers, it's going to take a little bit longer to get to the CPU. L3 cache is on the order of tens of megabytes. And then finally, what most of us would consider to be the bottom of the hierarchy is the DRAM. So those are the memory DIMMs. And there, it takes on the order of hundreds of nanoseconds to access that data. So we could see that we're always better off having data either in the registers or in one of those levels of the cache. Because when we have a cache miss and we have to go all the way out to memory, our processor is going to be sitting idle, waiting for that data to arrive. So, giving some specific numbers for Expanse. So this is for the EPYC, AMD EPYC Rome CPUs that we have. I'm showing here the L1, L2, and L3 caches. So L1 has capacity of about 32 kilobytes. And if data is in the L1 cache, it's going to take 4 clock cycles, or about 1.8 nanoseconds, until that's available to the CPU. L2 cache is 512 kilobytes. That's about 12 clock cycles away. L3 cache, about 16 megabytes, and that's 34 cycles away. And finally, if we go all the way out to DRAM, where we have on the Expanse compute nodes 256 gigabytes of memory, that's about 270 clock cycles away. So even though 120 nanosecond latency may not seem that large, to the CPU, it looks very, very far away. So what we're going to try to do when we're optimizing our code is take advantage of what we call temporal and spatial locality. So the principle of temporal locality is that data that was recently accessed is likely to be used again soon. So if we want to take advantage of temporal locality, once we load data into cache, it's going to remain there until it has to be purged to make room for new data. And cache is typically managed, and this is done by the CPU, not by the programmer, using a variation of a least recently used algorithm. So data that's in the cache that is the stalest is going to be pushed out first to make room for new data. The concept of spatial locality is that if a piece of data is accessed, it's likely that neighboring data elements in memory will also be needed. So to take advantage of spatial locality, cache is organized into lines. I say here typically 64 bytes. I have to say over the past few decades, I've never seen any processor that's used anything other than 64 bytes, and the entire line is all loaded at once. So our goal in cache level optimization is going to be to exploit these principles of temporal and spatial locality. And I'll make this a little more concrete in the next few slides. So let's talk about one-dimensional arrays. So 1D arrays, they're going to be stored as blocks of contiguous data in memory. So if we look at this little snippet of C code, let's say that we're going to allocate an array of 100 integers, and we'll assume that these are 4-byte integers. The elements x0, x1, x2, and so on, they're all going to be stored contiguously. And what I'm showing here, the numbers above the figure, these are the offsets. So element x0 would be at an offset of 0. Now we don't know where it's actually going to be in memory, but we do know that element x1, x2, x3, and so on are going to be contiguous. So if we're working with 1D arrays, cache optimization is going to be straightforward, and you're probably going to write optimal code without even trying. When possible, just access those elements in order. So in this little snippet of C code, we're showing a loop where we're taking each of the elements of the array x and we're incrementing it by 100. So what's going on when we execute this code regards cache? So assuming a 64-byte cache line and 4-byte integers, once we enter the loop, we're going to take elements x0 through x15 and we're going to load them into cache. So they're going to reside in the L3, L2, and L1 caches. Then we're going to increment x0 through x15. And now, when we go to operate on element 16, we're going to need to load in that next cache line. So we're going to load that cache line, and now we're going to increment elements 16 through 31, and so on. Now, in reality, the processors are smart enough to recognize patterns of data access, and they are generally going to prefetch that next cache line before it's needed. Now, one of the questions that usually comes up here is, do I have control over cache? Now, if you're working in C or C++, there's a mechanism for prefetching data so that it's in the cache when you need it. And this is the double underscore built-in underscore prefetch function. But there are no programming constructs that give you fine-grained control to specify which cache line should be replaced. So modern processors, they directly implement advanced cache replacement strategies. They also do things like branch prediction and prefetch mechanisms. So I'm going to say your best option is just to follow standard practices, exploit temporal and spatial locality, and in some instances, maybe choose optimal parameters for the size of your arrays based on cache sizes. Now going to multi-dimensional arrays, this is where things get a little more complicated. There really is no such thing as a two-dimensional array. It's what we call syntactic sugar, provided as a convenience of the programmer. Under the hood, multi-dimensional arrays are stored as linear blocks of data. Unfortunately, there are two different conventions. So it's sort of like driving on the left-hand or the right-hand side of the road. There's column major order, which is where the first or leftmost index varies the fastest. And this is what's used in Fortran, R, and MATLAB. So let's say I have this two-dimensional array with elements 1 through 9. The way they're going to be laid out in memory is we're going to go down the first column, 147, the second column, 258, the third column, 369. Row major order, is where the last or the rightmost index varies fastest. And this is what's used in Python, Mathematica, C, C++, any of the, I believe Java also, any of the C-like languages. So here, again, looking at that same two-dimensional array, we're going to go across the first row, elements 1, 2, 3, then the second row, 4, 5, 6, third row, 7, 8, 9. So this is really unfortunate that we have these two different conventions. It would be great if every language followed the same convention, but that's not going to happen. Sort of like driving, whether it's the left hand or the right hand side of the road. This is really, really baked in. If C decided to start using column major order or Fortran row major order, all of the optimized code that's out there already is going to stop running well. So you just need to deal with it. Now, next example is going to show how we can work with these multidimensional arrays. So I'm showing on top a properly written piece of Fortran code to add two arrays, and below that a segment of properly written C code to add two arrays. So note that the loop nestings are different in these two cases. In the Fortran code, I have do j equals 1, then do I equals 1 to n, and then I'm adding the arrays element by element. Z of ij equals xij plus yij. When I go down to the C code, notice that the loop nesting is reversed. My outer loop is over the first index, I equals 0 to n. The inner loop is over the rightmost index, j equals 0 to n. All right, so let's go ahead, look at the impact of using correct and incorrect loop nesting. And if you go to the example that's on, to the GitHub repo that's on the title slide, you'll be able to access the code and go through these examples on your own. So we're going to look at C or Fortran codes using the Intel compiler and the AMD compiler. And we're going to be concerned with compiler flags that control the overall optimization level and the target architecture. So pretty universal that C and Fortran compilers will have optimization levels. They're called -O0, O1, O2, and O3. And there's also a default. And that's going to vary from compiler to compiler. If you do -O0, you're going to get very, very slow code where absolutely no optimization is done by the compiler. A -O1 is going to be a limited optimization. -O2 is going to be moderate, and -O3 is aggressive. The difference between moderate and aggressive is that as we go from -O2 to -O3, the compiler can make modifications of the code that may change the order in which math operations are done. So it's going to preserve what we call algebraic identities, but when we're working with floating point math, floating point arithmetic, the order of the operations can give us a little bit of round off one way or the other. Now, if your code is well written, if the algorithms are stable, you should be able to use -O3, but sometimes users will stick with -O2. Now, the compilers themselves, we're going to contrast the AMD compilers with the Intel compilers. In both cases, we want to specify a target architecture. In this case, it's going to be the AMD EPYC processors using the Zen 2 instruction set. This is going to be specific to the processor, and the syntax is just a little bit different whether we're using AMD or Intel. Okay, so we're going to look at the impact of data access order. So I'm looking here at the runtimes for adding two matrices of size 30,000 by 30,000 using a Fortran code with loops nested in the proper and in the improper orders. So this is going to be a memory-bound application since we're only doing one addition for every two 8-byte floats that we load. And we're going to contrast the behavior of the AMD optimizing compiler, the AOCC compiler or FLANG, and the Intel Fortran compiler or iFort. And you'll notice here, let's look at the table on the left. For the AMD compiler, you'll notice that when I have the proper loop nesting, that my performance is always better than when I have improper loop nesting, and it also increases, the performance increases or the runtime decreases as I increase the optimization level. When I go from O2 to O3, you see that there's no difference. That's because once I'm at that level of optimization, there's really nothing else that the compiler can do going from O2 to O3. For the for the Intel Fortran compiler, notice some really, really surprising results here. We'll see that the default gives us the best performance, runtime of 1.19 seconds, and it's equivalent to using -O2 or O3. You'll also notice that for the default -O2 or O3, the runtime is the same for both the proper and the improper order of loop nesting. Whereas with the AMD compiler, there's a clear difference. So what's going on here? With the AMD compiler, as I mentioned, runtimes improve as we enable higher levels of optimization up to -O2. The default appears to be the same as disabling all optimizations. And this is a really, really key point. I mentioned that the default can vary from compiler to compiler. For many compilers, the default is -O2. Here, for the AMD compiler, if you do not specify an optimization level, you will get -O0 and you will have the slowest running code. Also notice the improper loop nesting is always slower than proper loop nesting at all optimization levels. Now the Intel compiler, here we see some very different behavior. The default appears to be the same as -O2. Also, the Intel compiler is smart enough to recognize that the loops are improperly nested and reorders them to get better performance. So if I go back a few slides, so if I look at the, if I had taken this Fortran code on top and I had reversed the order of the loop nesting. I have do I equals 1 to n, and then do j equals 1 to n. The compiler was smart enough to recognize that that code was was written inefficiently, and it re-nested those loops. So a few lessons to take away from this is making optimal use of cache is particularly important in these memory-bound codes. That's how we were able to do so much better, say with the AMD compiler, using a proper loop nesting, or with the Fortran compiler, in the case where it was able to recognize badly written code and reorganize it. And the second thing to take away is that sometimes the compiler will help you. In this case, the Intel compiler did, and sometimes it won't. So I would say to make sure that you get good performance with every compiler, with every hardware, make sure that you write efficient code to begin with. Don't count on the compiler helping you out. Okay, so we're going to look at some more loop level optimizations here. And let me just pause. I'm going to take a look again at the chat. And okay, no new comments. All right, so I know we're running a little late, but I'm going to go through some other loop level optimizations that we could do. One of the most basic is what we call loop fusion. This is where we take two loops that have the same range of iterations and we combine them into a single loop. So here on the left, I have two loops, I equals 0 to n, and I'm doing some operations involving arrays x, y, and a. So I'm saying z sub I is equal to x sub I times y sub I plus a sub I. And in the next loop, I'm setting wi equal to xi plus yi times ai. So in this case, we took those two loops, we fused them together into a single loop. So when you fuse simple loops, this gives the compiler more opportunities to rearrange instructions and get better performance. And also, if those two loops are operating on the same data streams, the same arrays, it gives us better data reuse. So if you look in the loop, if you look at the fused loop on the right, you know, the two assignments to array Z and array W, they're both operating on the same arrays, A, X, and Y. So in this case, when we're doing the calculation to update Z sub I, we've loaded X sub I, Y sub I, and A sub I into cache. In fact, it's going to be in the registers. And then for the next operation, it's going to be immediately available. So we don't need to worry about moving data into cache again. And if we look at the impact of doing this, and here we're just going to focus on the couple of bottom lines for the AMD and the Intel compilers. We'll see it's kind of modest, but in both cases, we do a little bit better if we fuse those loops rather than leaving them unfused. So it gave us about a 40% speed up for a very, very simple optimization. Let me just take a look. I saw again that we had a comment come in here. Yeah, so there's a question from Jonathan. Are there any reasons not to always use O3 optimization? Does more optimization increase compilation time? So two very, very good questions. I would say in general, you want to use -O3. But keep in mind that as you go from O2 to O3, your results may be very, very, very slightly different. So if you're familiar with floating point arithmetic, you know that floating point numbers are not stored to an infinite precision. So if we're doing what we call double precision arithmetic, standard math for scientific computing, we have 64 bits to represent those numbers. So now if we rearrange math operations, we can get very, very slightly different results. Now, if you find though, going from O2 to O3 results in a significant change, I would go back and look at your code and revisit the algorithms. So in general, I would go with O3, but I would test with both O2 and O3. And then, does more optimization increase compilation time? It does. So for most applications, the time that you spend in compilation is really small relative to the time that you would be running the code. But I've been working with a very complex chemistry application where going to O3 actually requires a lot of compilation time. So it is going to take a little bit longer, but I would say in most cases it would be worth it. Great, so excellent questions, Jonathan. Okay, well, moving on, I'm going to go a little bit faster here. So, I'm sorry, let me just see the chat again. Oh, good. All right. Loop fission, this is the opposite of loop fusion. Sometimes if the loop body is too complex or contains too many data streams, splitting can improve performance. Often difficult to decide if loops should be fused or split, but if this is a routine if these loops are found in a routine that was identified to be very computationally intensive, I would try both and see which is faster. There's something called loop invariant code motion. This is just a very fancy way of saying taking a calculation, an invariant calculation out of a loop, and using a pre-calculated result in its place. Sometimes the compilers can do this for you, but we still recommend doing it for yourself, as we saw with the example of the properly and improperly nested loops. The compiler may not always save you. So we're going to start here with a really straightforward example. Let's say that I'm looping over the elements of the array Z, and I'm assigning x sub I plus the square root of a constant. Square root operations are relatively expensive, and I'd rather not calculate the square root of that constant for every loop iteration. So I could take that calculation, I could move it outside, I could assign the square root of c to a variable, let's call it sqrtc, and then I can use that inside the loop. So there are no downsides to doing this, and potentially big savings. Now, where the compiler is not going to be able to help you is when there's less obvious examples of invariance. And these invariants may sometimes even be a vector results. So this is an example that I adopted from a code that I had optimized working with the US Geological Survey and the San Diego Zoo. So we have a kernel here with 3 nested loops, where I'm looping over the x dimension, over the y dimension, and z dimension, so over a 3-dimensional grid. I'm calculating the quantity x squared plus y squared, calculating the quantity z squared, and then I'm doing this calculation e to the minus az squared times the square root of b times x squared y squared. The actual calculation was a little bit different, but I just simplified it for this presentation. So if we start off, we could see that the quantity x squared y squared does not depend on the index k. So I could take that and I could pull it outside of that innermost loop. And likewise, the square root of b times x squared y squared does not depend on the index k. So I could move the calculation of x squared to the outermost loop nesting. So now we're only evaluating that nx times instead of nx times ny times nz. And then I could also take the square root of x squared plus y squared out one level. So now we're only evaluating it nx times ny times instead of nx times ny times nz. So this is going to give us a lot of savings. And you can see now the work that I'm doing in that innermost loop over the index k has greatly been reduced. But I could go a step further. We notice that z squared does not depend on the indices I or j. And similarly, e to the minus az squared does not depend on I or j either. So I could pre-calculate this entire vector of results. So I'm going to call it z term, which is e to the minus a z squared. And then instead of doing that calculation over and over each time within the innermost loop, I'm just going to refer to the element of that array. So doing this, doing these kind of optimizations in the code gave us a speed up of about 40 to 50x. All right, we're going to look at a few more optimizations. There's something called loop peeling. This is where we take one or more iterations, usually an iteration that's doing some sort of special calculation and pulling it out of the loop. It also allows us to fuse loops with slightly different iteration ranges. So let's look at the code on the left. We have iteration over index I. And inside that loop, I have one special case. If I is equal to 0, then z is going to be x divided by y. Otherwise, z is going to be x plus y. Again, this is a very, very contrived case. I simplified this for the presentation, but this is something that actually comes up a lot in real codes. And then let's say that we have another loop following that, where we're looking at I equals 1 to n, updating the array w. So here, by taking that special calculation and pulling it out, and then also changing the range of iterations, I was able to do two things. I was able to peel off that special first iteration, and I was then able to fuse two loops that had the same range of indices. And this is something that actually comes up very often in scientific and engineering codes. And then finally, one more example of a loop level optimization is something called loop unrolling. This is where we take the body of the loop and we replicate it. And then we will loop over a larger stride. Now, I'm going to say that this is something that you generally don't want to do yourself. Compilers are excellent at doing loop unrolling. It requires some significant modifications in the code. In this case, I took the loop body, zi equals xi plus yi. I replicated it 4 times, and I changed my stride from 1 to 4. This gives the compiler a lot more instructions to work with. It can rearrange them. It can get you better performance. But I'm going to say that you're rarely going to beat the compiler. Although, in some rare instances you can. And this is an example from a real computational chemistry code where the body of the loop was so complex that the compiler wasn't able to accurately analyze it. And I did a manual loop unrolling and was able to do significantly better than the compiler. Now, again, this is something that I'm not going to recommend doing often, but sometimes if you're looking at a particularly computationally intensive piece of code, this can get you a significant speed up. Now you might be wondering why I was talking so much about loop level optimizations. And the reason is this is where your code is going to be spending most of its time. In a loop, especially when you have nested loops, this is where you're doing most of the calculations. So these loop level optimizations are going to give you the biggest payoffs. And I'm going to show one more example, and this again was from a code that I had worked on, a collaboration with the University of Illinois on a computational finance code. We had a loop, and I've greatly simplified it here. But I say that if we meet a certain condition, say y sub I is less than a constant, we do a calculation. But this is a case where my colleague and myself, we knew something about the semantics of this code. In particular, that the elements of the array y are monotonically increasing, so that we know once we encounter this condition, what y sub I is greater than or equal to a constant, that we do not need to do any more iterations of that loop. We could break out early. And this is where we kind of make a transition from these generic optimizations to optimizations that are really specific for your code. This is an example drawn from a collaboration that I did with NCAR, National Center for Atmospheric Research. They had a new unstructured climate and weather code, where the domain was broken up into mostly hexagonal cells with a small number of pentagons and heptagons. So it's mathematical proof that you cannot completely cover a sphere with hexagons. You're going to need a certain number of pentagons or heptagons to make it work. And what we did was we recognized that in this case, the vast majority of the cells for this simulation were hexagons. I think it was well over 99.9%. So what we did was we took the original code, we retained that as what we call a default case. So for anything other than a six-sided cell, but then we split off and we optimized that special case where the cell is hexagonal. And I believe this gave us about a 40% speed up for this key routine in this climate and weather code. Some other optimizations you could do. One of my favorites is force reductions. This is where you look for a less expensive equivalent to a more expensive calculation. We know we're getting very close in time, but I'm going to point out that there are some intrinsic math operations that are very expensive. Square roots are more expensive than multiplications and additions and subtractions. Trig functions could be relatively expensive, and exponentiation could be very expensive. So if you have a case where you can replace a exponentiation, say in this case raising x to the 8, with a series of multiplications, that's definitely something that you want to do. And when it comes to trig functions, you might want to go back to your high school math. Sometimes you might be able to replace one set of trig functions with a less expensive equivalent. Just make sure that the identities apply to all the quadrants. So some of these optimizations, I had applied this to a small astrophysics code about 15, 20 years ago. And just by using my knowledge of high school trigonometry, I was able to speed up that code by a factor of about 3. For force reductions, look for hidden opportunities. We saw that example earlier where we're calculating the square root of a constant inside of a loop. That one was pretty obvious. But here, we could see on the left, we're doing a comparison of the log of x of I against a constant. We really don't need the logarithm of x sub I. We're just doing this comparison. Instead, we could have pre-calculated e to the c, save that as a constant, and use that in the comparison. So a lot of times we're concerned with what's going on inside of the loop, but we do want to be aware that any calculations that are being done in the logical tests are also going to take us time. And getting a little short on time, but here's an example where we're able to do a force reduction. Instead of comparing x squared plus y, instead of comparing the square root of x squared plus y squared to a constant, we compared x squared plus y squared to that constant squared. So, and this example is also available in the GitHub repos. Interprocedural optimizations, I really won't have time to get into this, but I'm going to say this is where you can sometimes have the very, very biggest payoffs. So this is where you need to take a high-level view of the entire program, looking across multiple functions. So your compiler could be great at optimizing loops, unrolling and fusion and splitting and peeling and so on, but it can rarely recognize the opportunities for interprocedural optimization. This is a very, very active area of research in high-performance computing, but it's also hard to do. And these sorts of optimizations often require that you have a really deep, intimate understanding of your code. So I'm going to just go through this very quickly. This is going back to that flow cytometry example I talked about earlier. But what we were able to do was look at multiple calls to a function, realize that there were calculations that were being done each time this function was called, And instead we could, and I know we're going through this too quickly, I was able to save results, which could then be reused and passed to modified versions of these functions so that it could be used over and over again. This is something that no compiler would ever be able to do for you. And by the time we're done, I believe we got about a 20x speed up on this application. So yeah, so we are right at the hour. So I'm going to wrap up. Say that optimizing your code reduces time to solution, saves energy, makes resources go further. Before you get started, make sure it's worth your effort. Is this a code that is heavily used? Is it widely used? Is it going to help you get your research done quicker? Getting back to, I think, is the question that Jonathan raised. Optimization as we go from O2 to O3, or manual optimizations, can sometimes change results. Remember that algebraic identities are not precisely floating point math identities. But you do need to ask yourself, how critical is reproducibility? Can you tolerate that potentially very, very small difference, often 8 to 10 decimal places out as you make these changes? If you are going to optimize your code, profile, optimize, and then after you're done, profile again. Take advantage of the optimized libraries and the work of others. We like to say that good programmers write good code, great programmers steal great code. So if somebody else has already implemented an algorithm you need, especially eigenvalue solvers and linear algebra and so on, take advantage of that. There are groups out there that have been spending decades trying to improve the performance of these key math operations. Know the capabilities and limitations of your compiler. So we saw in that example earlier, looking at the addition of two arrays using proper and improper loop nesting, that it can have a big impact on the performance. In one case, the compiler recognized your bad programming and fixed it for you. In the other case, it didn't. So, be aware of this. And I would say sometimes take your code and compile it using two different compilers. If you see drastically different performance, that may indicate that one compiler is recognizing some bad programming practices and fix them while the other hasn't. Optimize for cache is critical. Exploit that spatial and temporal locality. And then finally, your biggest payoffs can come from a deep understanding of the semantics and the structure of your code. So with that, we are just past the top of the hour, and I'll leave these links up. Of course, this is in the presentation. You get access to the full half-day version of performance tuning and optimization on our Summer Institute page, and we have the example code that was used in this presentation. And with that, I'm going to stop sharing and see if there are any more questions or comments.